So the solid um, out of today's objective, but the word embedding, so this is called the word embedding technique, right? The previous one. So by having the representation, we have the coordinate about the queen, the woman, right? And we have some vector. So for example, this is three-dimensional vector. It will plus some directional some vector. This is also three-dimensional, and then we can get something, right? So when we add this one to woman, we were able to get the man, the representation of man. From this observation, we add the same vector to queen, and then we were able to get the king. See, they found that this semantic relationship could be learned from the word embedding. This is also called the word analogy task. So this is one of the hard tasks from the word embedding. So this technique dramatically improves the previous state of the art, and people surprised that and now developed a better idea, but the word embedding is still a very meaningful and important milestone. And the big and small, biggest, smallest, also similar relationship, but this is from the syntactic, I'm sorry. So from the similar vector addition computation, we can sort of infer the syntactic relationship. So this is just case. So we get the representation from the word, and to apply one-dimensional CNN, we can classify the labels of the sentence or document, right? In this case, document. So we do the sentiment classification from the word embedding. So nowadays, people use BERT, right? GPT or so. So you see, the representation learning is currently dominant in deep neural networks. So when you see, so even the image classification, natural language processing, the representation learning is the key idea of the deep learning. So from the massive data set available, we learn the raw dimension representation, such as the word embedding, the BERT and GPT, right? So we get the better representation, and maybe autoencode for the image data set, and then we train or fine tune the model for the learning objective, right? The downstream task. So that is the key success factor for in this deep learning era. So here's our question again. So how to leverage the success, the representation, the success from, so specifically the word embedding success in the graph data. But apparently we have different input, right? In the case of the natural language, what is the input? They are sentence, right? It is sequentially presented, sequential information. The speech is also sequential information, and image is also, but not sequence, but two-dimensional. It could be defined. It has a locality about the up and down and left and right, but they all could be defined in the Euclidean space, right? But adjacency for the graph data is not possible to represent in the Euclidean space. So to leverage the success, people start think differently. So we have the input output in this word embedding model, which is also called the skitgram based model. And we need to have the input and output. They are from the sequence in nearby the neighbors from the WI. So what is the case? What is the comparable observation in graph data? So obviously word could be node, right? Should be node, and output, their context, the neighbor, could be from the random walk. This is the initial trial. What is a random walk? For people who are not familiar with the random walk, and I prepared this example. So this is a drunken guy sit here, and he has 3 possible ways to work. How to work? So 3 possible choices. So we have 3 possible choices and just randomly choose, uniformly choose some of them. Let's say we chose this. We have the first work, and now we have just one choice, and we work another. The second as a second work, and then now we have 2 different choices, right? And we choose this one as a third work. To look back, and we have a path. This is called one instance of random walk. Random walk, RW. I'm sorry, RW. So this could be the context of the node, and you can substitute the sequence of the words for applying the graph data for applying the word to bank model for graph data, right? So once again, word is converted to the node to get the node representation, and instead of the sequence, and we use random walk for the context of node. So that's all. You can close this lecture if you understand this. So here's more details, and we have input. This is more mathematical, the more formal representation. In G, we have X. Now we understand the meaning of this representation, right? And now we have the random walk or node path. And the VI came to here, the path came to here, and use the same skitgram, and we get latent region matrix. So super easy, but that was the honestly the only contribution, the KDD paper, but it became the most cited paper. I think this number of citation is more than 10,000, maybe more than 20,000. Could be something like that. Yeah. Check it out and let me know. So let's step further about the optimization. So if you understand the optimization, the skigram, so you don't need to watch once again. So now we have the VI as an input, and we have their context. So VI is the input, this is the output as a context, right? So the pi represents our initialized region matrix. So instead of the ID, so this means the k-dimensional the feature block value. And so think about your neural network. So we use the input as for the VI and try to maximize, try to predict the ID of the context. So instead of just simply use the ID for the input, and we can use the current representation of VI. We keep updating the feature matrix during the running, but from the initialization, I would say random initialization, they have some own their representation and try to predict the sequence ID. So this is objective. So we keep developing from this objective, right? We usually do not think about this right now. From this, we try to maximize probability about the appearance of this context node, right? We try to maximize. It's straightforward, right? From this, we try to predict their neighbor, the context, right? Instead of the maximize, we put just negative and minimize. We try to choose this matrix, right? We try to look for the latent matrix which minimize this value. We just put the logarithm as well. So this is the objective of deep work. So this is the algorithm. We have input, right? So they are, so we have a window size and embedding size, the work length. The window size means, so we have this random walk. So let me start with the walks here. Walks means from some input I, we have in this case 1, 2, 3, 4, 5 sequence as a neighbor, and this size is the number of walks per vertex, right? This one. Embedding size, the previous k, it was k. And window size is maybe we use this, for example. So we choose one of them. So I don't want to be complicated right now. So in the skigram, so they use the nearby nodes. So even though our input sequence is composed of the 5 different neighbors, but in the actual running, it could be reduced into, for example, 3 or 2, right? So this is called the window size. And previously so explained the wrong information. So walk length is a random walk length. In this one is how many random walk is generated from the random walk process. So For example, in the drunken man, we get this as a first random walk. We get this from second random walk. We get this from third random walk. So 3 is the number of walks in here. Yeah. And this is our expected output. We initialize randomly the latent representation, right? This is also called the latent representation. So I try to use the one terminology, but yeah, for your information. So the vertex representation, and we initialize randomly. So we just ignore this right now, and maybe this is for the random generation. So we get the VI from some shuffling process, and we get random walk, and then learn skigram, and we get random walk and learn the skigram. So this is the simple learning procedure. So we are also interested in the details of skigram here. So you can find all the details in the deep work paper. In skigram, we have the input node, we have the context. Context is from the random walk here, right? This is random walk. In the random walk, we choose the sum of them. I'll say so in this case, so I didn't want to be complicated, but the randomer, the VI and V here WVI in the randomer, in the middle of the randomer, it could be the input node. So not always start with the here. So just pretend to we know the process. So let me give you just the brief idea. So we have random walk. We have the input node here, and we have context as a sequence, and we can determine the window size. We just get in this case, so for example, this we put this is 3, and we get 3 left the neighbor and 3 right neighbor from the random walk, and we use their pair J and K and J and K. We use this information to update the latent representation using stochastic gradient descent. So in this case, we have another objective function, right? So instead of this, so we use I and Vi minus W. So it is sort of pairwise optimization. I and J, the one of the context nodes, and I and I by plus 1, for example. So we choose I and UK, and UK is from the context random walk, and we try to minimize this J, and we can update the the actual feature matrix. So this is the trainable the matrix. So this is the procedure. So actually, this is not the entire objective function of the random walk. That's why you may feel confused. So this is directly from the paper. So the original objective function is not like this. So that's why you may be difficult. I also difficult to explain. So they're the same. Just in this page, you just need to understand. So objective function from the schistogram. We get the input and output the random walk, and we update the feature matrix. Just understand that procedure. So let me give you details. Actually, I prepared all the details about the learning. Right? Hopefully, you don't much be confused about it. So let's come back to our notation here. Once again, we have z. So here the pi is same as z in this case. We have z here. This is our target trainable matrix. The z is same as this one, right? So for optimization, so we previously have this one. So everybody understand this, right? From the input and try to maximize the output, but we put minus and minimize, right? So instead of the output, the random up, so I'm using the neighbor function. This represents the sets of neighbors from the input. This is the input, the z, and everything else is same. So we try to get the f, which minimizes the following objective function. And to get the representation, so we need to get the the row value, right? So this is the youth, and this is same as the function f of u. This is a functional form of the representation, and from the maximum likelihood optimization perspective, so it is same as this one, just remove the max in this and maximum likelihood estimation, right? Just for your information. And once again, this is from the random walk neighborhood of node u. Equivalently, so from this, so when we consider the all u to define the loss function, so in this case we dealing, so this represent whole the representation, but now we summaze all the negative log likelihood over all the possible log value, and this also need to summaze from all the possible random walks, right? So now we have this objective function. That's why previously we have something like this. So now we understand, right?